Chapter 9, Introduction to Hypothesis Testing, Section 9.1, Definitions and Notation. So we're going to start off with the definition of a hypothesis, and that is just a statement that something is true. You've probably heard before that a hypothesis is an educated guess, and we certainly could go with that as well. But when we do hypothesis testing, we want to be able to test claims that are educated guesses. We also want to be able to test or challenge a claim that's kind of a wild claim or guess as well. So any statement that something is true can be considered as our hypothesis. In a hypothesis test, there's two different kinds of hypotheses involved. One of them is called the null hypothesis, or sometimes you could consider it to be the initial hypothesis. That's denoted by an H with a subscript of 0, or H sub 0. And this is the hypothesis to be tested, and by that we mean challenged. And this hypothesis sets some specific value for either the population mean or the population proportion, and that specific value is usually one that is claimed, old, or comparable. Or in some cases it might just be a default value. So maybe somebody's claiming that they know what the average age of students at a college was 5 years ago. That would be the old one. Maybe somebody's claiming that their Pepsi cans contain 12 ounces of soda in them. Maybe we have a claim about what is going on in the state of Arizona and we want to compare California to that. And then we'll see some cases where nobody's really making a claim, but we need a null hypothesis, so we'll set one up as a default. All of those will show up. The other claim in a hypothesis test is called the alternative hypothesis, and we denote that with an H subscripted with a 1, or H sub 1. And this is the hypothesis to be considered true if HO is shown to be false. Remember, we're challenging H sub 0, so we're kind of attacking that one, trying to show it's a false claim. And if we succeed, then H1 will be the one that takes over in its place. This is also the claim that we're trying to prove, and this claim never includes the possibility of equality. So a few things we're seeing early on here with these hypotheses is that this one right here sets a specific value, so this one will contain equality, and the alternative never includes that possibility of equality, and we'll see how that carries out. And then it also says this is the claim we are trying to prove. So I would say that if you wanted to think about this as two teams, this one's us, and H0 up there is them. And it's good to know what team you're on when you're in any sort of competition, so I would say that's true here. And we'll kind of use this idea as we go through the hypothesis test that we look at in this chapter. Alright, let's go ahead and look at an example that just talks about how you would set up the null and alternative hypotheses and how you decide which is which, and then also to see a little bit of the logic about how hypothesis tests work as well. So let's jump down into this example. People in California feel that they are being charged a higher price for gas than people living in other areas of the country. In August 2009, a study showed that the average price for a gallon of gas in the U.S. is $3.097 per gallon, and a local newspaper wants to perform a hypothesis test to determine if the average price in California is higher than the national average. And for some stuff we're going to do later, we'll assume that sigma x bar is approximately $0.024806. So determine the null and alternative hypothesis for this situation. So the first thing we have to decide on a hypothesis test, is it a claim about a proportion or an average? And we see here that we're trying to determine if the average price in California is higher than the national average. So we see the word average mentioned a few times. And so when we set up our claims, they're going to be about the population average. So both H0 and H1 will be about the population average or mean, which is mu. And then one of the things that we said kind of quickly and briefly up here with the null hypothesis is that it sets a specific value for the mean and proportion, which means it's going to make the statement that mu is equal to some value. So now we reread the problem and we look to see, is there some value for the mean that is being claimed or mentioned somewhere? And it says a study showed that the average price for a gallon of gas in the U.S. is $3.097. So what we're going to do is let that be our default or initial value that will put in H0 for the mean price of gas at 3.097. Now for the alternative H sub 1, we try and look at what is it that we're trying to show, or even that somebody is trying to show, that doesn't include equality. And we go back and look at the words for that again. It says this newspaper wants to perform a hypothesis test to determine if the average price in California is higher than the national average. So that idea that it would be higher than the national average would be that the mean is actually greater than that 3.097. And notice that we're not using an equals in H1. So the equals goes in H sub 0, and in H1 we will never have an equal sign. And that's our null and alternative hypothesis. Now when we talk about the us versus them, I actually do not think about that when I'm trying to write these down. I think about an equals in H0 and looking for a word that does not contain equals to go in H1. But now that they're set up, I know that, okay, H1 is going to be the one I'm fighting for, H0 is the one I'm trying to show false. Alright, so now that we've gotten those set up, let's look a little bit at the logic of a hypothesis test. In part B, they want us to provide a value for the sample mean that would provide some evidence for H1, but probably not enough to lead to the rejection of H0. So to explain how that works, I have to tell you what a hypothesis test would be like. We would be trying to show that the mean in California is greater than 3.097, and to do that we would go out and get a random sample of some gas stations and get an average gas price. So that average we get from a sample, and talking about a sample mean, would be an X bar. So what kind of X bar would provide evidence to support our case? And you have to remember whose side we're on, or H1. So if we got an X bar that was greater than 3.097, that would provide some evidence that H1 was false. Whether it's enough to lead to the rejection of HO depends on how far to the right it is. So, for example, if I were to get an X bar of, let's say, 3.11, so $3.11 from my sample, then that would provide evidence against HO and in favor of H1 because my mean is bigger than 3.097. But the problem is, I don't know why I got a mean bigger than the national average. Maybe it's because California has a higher price, but on the other hand, it might just be a random variation. So to think about that, I think, well, how many standard deviations away from this is it? And it's about a penny above the claim value. Well, the standard deviation is about 2.5 cents. So anything that's within 2 standard deviations of this claim value, it'd be possible to say, well, that difference might just be random variation. And when that's the case, we say that's not enough evidence to lead to the rejection of HO. So let me show you that on a picture. Assuming I took at least 30 gas stations in my sample, then the X bar would turn out to be bell-shaped. I would give the benefit of the doubt to H0 at first and put its claimed value of 3.097 in the middle. And then I think about where's this 311. And it's on the right, that's why it provides some evidence for H1. But it's not way out to the right. 2 standard deviations maybe be about here. That'd be about 5 cents to the right if you double that. We're only about a penny past, so we're getting an X bar like somewhere around here. And if you're on the right but not way out in the right tail, we consider that weak evidence. So a small difference, which this one is weak evidence. It's evidence because it's greater than the claim value, which is what we're trying to show, but it's weak evidence because it's a small enough difference that it could just be random variation. And I think we'll get a little clarity there as we look at the next part. Provide a value for the sample mean that would most likely lead to the rejection of HO. So in order for us to reject this claim H0 that mu is equal to 3.097, our sample value couldn't just be to the right, it would have to be unusually far to the right. And so usually we set that value at 2 standard deviations. To be safe here, I'm going to go 3 and make it extremely unusual. So if I took this standard deviation of basically 2.5 cents and tripled that, that'd be about 7.5 cents. So what I'm going to do is I'm going to pick an X bar that's about 8 cents, even more than 3 standard deviations to the right of that. So let's call that $3.10. Add 8 cents onto that. I'm going to say if my X bar came out to be about $3.18, that would not only support H1, but it would convince me that HO was false, or at least convince me beyond a reasonable doubt. So So let me go ahead and draw that picture. So I'd still do the bell shape, assuming we have a reasonable sample size of 30 or more gas stations. I'd still put that 3.097 in the middle. And the reason I'm saying this evidence is strong is because it's not just on the right side, it's unusually far out there to the right. This value of $3.18 looks like it's more than 3 standard deviations to the right of the mean. And what we've learned in chapters like 3 and 5 and 6, 7, 8 is that it's unusual, very unusual in fact, to have a sample mean land more than 3 standard deviations to the right of the mean just due to random chance. And if we don't think the reason we're landing that far to the right is random, then another possible explanation which we'd want to look for is that maybe the mean isn't really 3.097, maybe the mean is greater than 3.097. So when we get a big difference, which we did here, that implies that we have strong evidence, and that would be, I think, strong enough evidence to be able to reject HO. Now at this point, we're just getting started with this. I'm just trying to give you a rough sense of how a hypothesis test works. We have a lot of details left to add as we go through the rest of the chapter, but our initial idea here is that small differences provide weak evidence because they could just be random variation, but big differences provide strong evidence against H0 because it's unlikely such a big difference would be the result of random variation. And we've said all along this semester that if a difference is so big it doesn't look like it's random variation, you seek an alternative explanation. H1 is our alternative hypothesis. It is the thing we're going to consider to be true if that one turns out to look false. Alright, continuing on with our example about the gas prices. They want us in part D to identify this hypothesis as left-tailed, right-tailed, or two-tailed. And the way we do that is we think about where would our X bar have to land for it to be considered strong evidence. So if we look back at what we just did on the previous page, to get small or strong evidence we said we have to land on the right, and in order to be able to reject we had to land out in the right tail. So when you're doing a greater than for your alternative hypothesis, in order for your data to support your claim, you have to get an X bar that lands on the right hand side. And so because of that, whenever our H1 is a greater than, we're going to say that we have a right-tailed test. So let's just go ahead and take a moment here now to recap some of the things that we've seen as we went through this first example. One of the things that we mentioned is that when you're writing H sub 0, the null hypothesis, that's always written using an equal sign. So every time you write that, it might be about a mean or it might be about a proportion, but it'll always have an equals in it. So our H0 said mu equals 3.097. You're always going to have that equal sign in your H0. And then the second thing is to decide on the symbol for H1. You should look for a word in the problem that indicates an alternative to a quality that someone is seeking evidence for. And we say someone because it may be you, but it may be someone else that's hiring you. In this problem that we looked at, it said that the newspaper wants to perform a hypothesis test to see if the average price in California is higher. So it doesn't matter really who it is that's doing the seeking or wants to see this. What matters is that we have an alternative to equality, and higher than would be this greater than symbol, so that went in H1. And then finally, we would determine if the test is left-tailed, right-tailed, or two-tailed just by looking at the symbol that is in H1. So just remind you of how we did that on the last one. Because the symbol was a greater than, I ended up saying that it was a right-tailed test. So you can always quickly know whether it's left-tailed, right-tailed, or two-tailed just by looking at the symbol that's in H1, and we'll see that as we continue to go through our examples. Alright, so let's go ahead and look at another one. In 2009, the Tea Party movement began in the U.S. The group got a large amount of attention from the press when they began rallying against President Obama's health care reform plan. In April 2010, CBS News conducted a poll to try to learn more about Tea Party members. At that time, it was known that 25% of Americans were college grads. We want to use the results of the CBS poll to see if the true percentage of Tea Party members that are college grads is different than for Americans overall. and assume that the standard deviation of p hat is about 0.015024. Alright, so they want us to determine the null and alternative hypothesis for this situation. And the first thing we always need to do on those is figure out, is this a problem about an average or a proportion? So we want to use the results of the CBS poll to see if the true percentage. So that seems like a reference to p rather than mu. So I'm going to say that for HO, I'm going to make a claim that p equals something. And for my alternative H1, it'll be that p is greater than or less than or not equal to something. So that's going to be my initial start. And to determine the null hypothesis H0, I want to find a value that I can set that p equal to. And so for that, I look at this problem and I see that it says at that time it was known that 25% of Americans were college grads. So they're saying that the percentage of college graduates was 25%, and this P stands for percentage of college grads. So I'm going to use that number here. It says 25%, but I'm always going to do my work in a hypothesis test about a proportion using decimals. So I'll write P is 0.25. Okay, so now for the alternative, we want to find something that somebody's stating that would be not an equal to 25. So let's see. We want to use the results of the CBS poll to see if the true percentage that are college grads in the Tea Party is different than. So that is different than doesn't say higher and it doesn't say lower, it just says it's different, and that means it could be higher or lower, and the way we denote that is by putting an equal with a line through it, which would be read as does not equal to 0.25. So the initial claim is that P is 0.25, the alternative is that no, it's not. Just a quick comment here. There's a tendency to think that this P in the first line is for Americans overall and that the P on this line is for the Tea Party members, but it's actually not like that. It's a left-right thing rather than a top-bottom thing. The P here that we're trying to talk about is the true percentage of Tea Party members, and the 0.25 is for all Americans. So maybe the percentage for Tea Party members is 0.25, just like it is for all Americans, or our alternative, maybe the percentage for Tea Party members is actually different than the percentage for all Americans. And so I would say here we're doing kind of a comparison, that this 0.25 is a comparable value. We know what it is for Americans and we're comparing it to Tea Party to say, is it the same for Tea Party or is it different? Alright, let's look at the follow-ups now. Part B, provide a value for the sample proportion that would provide some evidence for H1, but probably not enough to lead to the rejection of HO. First of all, I just want to point out sample proportion. The symbol for that is P hat, and it's good to see a P hat when we made a claim about P. Those fit together. Just like last time we had a mu here and we got an X bar on this line. So you always want to be talking about proportions in both places or means in both places. If they don't fit, you might have made a mistake up here or you might be making a mistake down here. Alright, so let's provide a value for that P hat that would provide some evidence for H1 but probably not enough to lead to rejection of H0. So as we saw in the previous example, what would cause that to happen is if our P hat was different than 0.25 but not a lot different. So how do we decide what's a little bit different, what's a lot different? Well, anything less than one standard deviation away from the claim value is just an expected, normal, small difference. So when they say they want it to be weak evidence, I want a small difference. Anything less than a standard deviation away from the claim value would be a small difference. So assuming that we had a situation where NP and NQ were both at least 10, the distribution of P hat would be normally distributed. When we do a hypothesis test, we always initially assume that H0 is a true claim, or at least give it the benefit of the doubt. And that means when we draw our curve, we'd have the 0.25 in the middle. And then what would be a value of P hat that would be different than that, but not different enough to make us reject HO? And again, the answer would be a small difference would be evidence in support of H1, but it would be weak evidence. And a small difference would be less than 0.015. So maybe if we got a P hat like 0.261, that's about 1.1% difference, smaller than a standard deviation. That would do it. Or maybe another option would be if we got something like 0.243, So that would be just 0.007, definitely less than 1 standard deviation. So values of p hat like this or like this, and you couldn't get both, would be one or the other. But if you had either one of those, they would be weak evidence. And again, the idea is that these are small differences because they're less than 1 standard deviation away from the claim value, and small differences provide weak evidence. This time I did make a point of showing the value could be on the left or the right, and the reason for that is because when our alternative is does not equals, anything different from 0.25 is evidence against H0, so that could be different because it's bigger or different because it's smaller. But again, these are small differences, less than a standard deviation, so they're providing weak evidence against H0. Alright, we're continuing on with our example about the Tea Party. And in this part C, they want us to provide a value for the sample proportion that would most likely lead to the rejection of H0. And if we just look back at our previous page, we said that the evidence would be weak and not enough to reject if it was within 1 standard deviation of the claim value. If we want our evidence to be considered strong, we'd probably want it to be at least 2 standard deviations away, or better yet, even 3. So I'll go ahead and draw my bell-shaped curve for the p hats. I'll put the claim value of 0.25 in the middle, and then I'm going to think about how big would the difference have to be so that it would be a big difference, because big differences provide strong evidence. And when we have that strong evidence, that's when we can reject HO. It's strong evidence that the difference we're seeing is not just random variation, that there's something else, and that we would go with the alternative. So let's see, the standard deviation of p hat is about 1.5%. So 3 times that would be about 4.5%. So any value of p hat that was more than 4.5% away from this would be considered strong evidence. So one example on the right, maybe if we got a value of p hat like 0.31, that would be strong evidence against HO, because that's about 6%, which is about 4 standard deviations away. Or maybe if we got something on the other side for a p hat like 0.201, that's about a 5% difference, which is again more than 3 standard deviations away. So we'll see more detail on this as we get into section 9.2. But when you see a big difference, that would be considered strong evidence. A big difference certainly would be one that's more than 3 standard deviations away, definitely qualifies as big. And when they talk about weak evidence, that would be one where the difference is small, and if your difference is less than 1 standard deviation away from the claim value, that would definitely be considered small. And then finally, moving on to the last part of this, identify the hypothesis test as left-tailed, right-tailed, or two-tailed. Notice that our evidence could be strong whether it was on the right or the left, so it could be in the right tail and we might reject HO, or it could be in the left tail. Since it could be in either of those tails, we fall into this category of having a two-tailed test. And we said after our first example that when you're trying to decide is it left-tailed, right-tailed, or two-tailed, you look at the alternative, and H1 has the does not equal in it, so whenever you see that happen, you're going to end up with the two-tailed test like we did here. Alright, let's go ahead and move on to another example. The price of snowboarding equipment generally falls dramatically as the season comes to a close. During January of 2008, the average price for a new pair of snowboard bindings was $138. A snowboarder/stat student wants to conduct a study to see if the average price of such bindings in April of 2008 has fallen below $100. So the first thing is trying to decide in HO, am I going to write mu or p? And I see average price right here, and let's see, average price right there. So we're seeing the word average show up there a few times, so it seems like H0 and H1 should be claims about mu. And then kind of glancing down a little farther, notice that they start talking about our sample values as x bar, which is a sample mean, which does fit together with the idea of using a population mean. So those are good clues that we're picking the right type of test to write out here. And then in HO, we're always supposed to put an equal sign, so I don't really have to read any of the words to know that part. I just have to think about what should I set it equal to. And this time that can be a little trickier than on other problems, because you have several numbers to choose from. You have the 2008, the 138, the 100. Well, first of all, this is about average price, so we can throw out 2008, which is a year. But even then, we still have $138 or $100. So which one would it be? It's not perhaps clear right away. And if you're ever in a situation where it's not clear, abandon H0 for a minute and go to H1 and try and write out what that one would be. So what is it that somebody's trying to show that does not include equality? And it says our snowboarder stat student wants to conduct the study to see or to try and show if the average price has fallen. Has fallen sounds like a less than to me. Has fallen below $100. So they're trying to see if the mean has fallen below or is less than 100. And if you look back at the problems we've done, you will see that the number that shows up in HO shows up again in H1. That was true in our first example. And it was also true in our latest example, 0.25 in both cases. That's always true in a hypothesis test, that you have the same number in both spots. So when you see that clear wording that we're trying to show that the mean has fallen below 100, that shows us that this should be 100 as well. We never have different numbers in those two places. So the 138 is actually just a bit of a distractor. That's just kind of some history on it. And if you think about it, if you're a skier or snowboarder, you would know that in April prices are cheap because the season's ending and stores are trying to get rid of their stock. So if it's 138 during January, which is the peak of the season, then of course it's going to be lower when the sales hit in April, but will it be lower than 100? That's what we're trying to show. Alright, so there's our null and alternative hypothesis. And so is this a left-tailed, right-tailed, or two-tailed test? Well, we've said a couple times now, you always look at the alternative H1 to decide that. We have a less than, and less than means we would need a mean that was on the left side to prove our case. So that would be a left-tailed test. And then here they're giving us some evidence and asking us if it's strong or weak. So assuming the standard deviation of x bar is 2.87, would you consider a value like x bar equal to 9782 to be weak or strong evidence against HO? Well, if I were to look at the difference between this and the $100, it looks like about $2.18. That's less than one standard deviation. So when we are getting a sample value for x bar that is less than one standard deviation away from the claim value, that's a small difference. And if it's a small difference, that implies that it's weak evidence. And again, the way you decide is it small or a big difference is by looking at how big is the difference compared to the standard deviation. So 100 minus 97.82 is $2.18. That's less than one standard deviation away, so that's a small difference. It's weak evidence against HO because even if HO is true, we could get a value like this easily just due to random variation. But assuming that same standard deviation, what if we got an x bar like 112.33? Now if we look at the difference between x bar and the mu that's claimed, and we'll see later that's referred to as a mu sub 0, then we would have 112.33 minus that 100 would be 12.33. And if the standard deviation is 2.87, that's going to go into this more than 4 times. And so if these two are more than 4 standard deviations apart, that's very strong evidence against HO because that's a really big difference, right? Anything over 2 standard deviations apart is unusual, so 4 standard deviations or more would be extremely unusual. So we have a big difference here. And a little bit of a trick question here actually. I was about to say that big difference would be strong evidence, but something tricky has happened here. That x bar is not landing on the left side. 112.33 is not less than 100, it's more than 100. So we are getting a big difference between the claim value and our sample value, but it's in the wrong direction. And anytime you get a sample value that's in the wrong direction, whether that is a big difference or a small difference, it's bad evidence. So this is on the wrong side because it's on the right and we're doing a left-tailed test, and anytime you're on the wrong side you've got very weak evidence. So that's kind of an interesting one, a little bit tricky, but this can happen sometimes. So I would have said it was strong evidence because we were 4 standard deviations away if it was on the left side, but because it's on the right, it actually turns out to be weak evidence after all. Alright, so we've looked at how to set up our hypothesis tests in terms of deciding how to write H0 and H1. We've looked at deciding whether evidence is considered strong or weak, and we've looked at how to decide if it's left-tailed, right-tailed, or two-tailed. Now we want to think about the kind of conclusions that you can reach in a hypothesis test, and there's 2 possible conclusions that can be reached. One of them is that you can reject H0, and as we kind of had come up in our discussion so far, you would do that if there was enough evidence to prove H1, and that would mean that you had a big difference between your sample value and the claim value, and that difference was on the correct side. Another thing that we could have as our conclusion is do not reject HO, and we would do that if there's not enough evidence to prove H1. And our evidence can be weak if it's on the wrong side, like for example on the right when we're doing a left-tailed test, or it might be on the correct side but just be a small difference. And in order to prove our case, we need strong evidence, not weak evidence, and strong evidence comes from big differences. I do want you to notice here, though, that when we talk about our conclusions, it's not reject H0 and accept H0, it's reject HO and do not reject HO. We never accept HO as the conclusion for our hypothesis test. And I want to give you a couple analogies to that. One of them would be that if you're doing a criminal trial, you might find the defendant guilty, but you don't find them innocent. So all the evidence that comes forth is trying to prove that the person committed the crime, and if we're lacking that evidence, then we have to let them go. And there could be times where a jury even thinks that the person on trial committed the crime but still lets them go because they feel like the evidence was not strong enough to prove the case beyond a reasonable doubt. So when we don't reject HO, it doesn't mean we've become convinced that it's true. It just means we don't have strong enough evidence to show that it was false. And then in a hypothesis test, the differences that we see between our sample value and the claim value are our evidence. And if those differences are big, it can prove that things are different than suspected originally in H0. But if our sample value comes out close to the claim value and the differences are small, that doesn't mean H0 is true. It might just be false a little bit. And an analogy to that would be to think about money. If you look at a dollar bill and it looks similar to the real thing, then maybe it's a real dollar bill, maybe it's not. But if you look at it and the differences are large, then you'd be convinced that it was not a real dollar bill. So if I slide this dollar bill in here and you start looking at it, you look at the corner and you see things like, maybe if you've heard this before, there's a little bird kind of perched on the corner and you see that and you're like, oh, real dollar bills have that, so maybe that's a real dollar bill. But just because it looks like one doesn't mean it is. It could be a real fake, maybe a real good fake. As I slide this over, it should become a little bit more evident to you that this one's not real. We're supposed to see George Washington, not Johnny Depp. Right? So when you see a difference, it proves that something is wrong. When things look similar, it doesn't mean that everything's okay. So we never have the accept H0 as a result, because even when things look right, like this does in the corners, it doesn't mean that it is in fact right. There could be differences somewhere else that we just haven't looked at. Alright, so in addition to our 2 conclusions of rejecting HO or not rejecting HO, there's also the question of, was HO true or false? And when you put those together, 2 possible conclusions, reject HO or do not, and 2 possible truth states that HO is true or that it's false, you actually end up with 4 different ways a hypothesis test can turn out. One of the ways is that you could reject HO when it is true. And if you think about that, that's a bad situation. Somebody's telling you a claim that's true, but you reject that true statement. That would be an error. So I'm going to write error in the bottom of the box, and as you do that I would encourage you to write it in the bottom as well, leave the top free. And then I'm going to go on to the other boxes. If HO is true and I do not reject it, that would be a better outcome. If somebody's telling me the truth, I don't want to reject what they're saying. So if we landed in this box where we didn't reject a true claim, I would say we had made a correct decision. And over here, if we reject a false claim, that also seems like a correct decision. What if somebody was telling us a lie and we rejected what they were saying? Then that would be the right thing to do, to reject that lie. But if they were lying to us and we didn't reject it, we'd let them get away with that lie. That would also be considered an error. And the way we set up a hypothesis test, we label the errors to distinguish between them. When somebody is telling us the truth and we reject that, we call that a type 1 error. And if somebody is telling us the lie and we don't reject it, we consider that to be a type 2 error. And you shouldn't necessarily take that to mean that one is more serious than the other. They're both errors. We don't want to make either type. We want to make correct decisions, but we want to distinguish between the two types of errors that can happen. So a type 1 error is rejecting HO when it was in fact true. And a type 2 error is not rejecting HO when it is in fact false. So not rejecting HO and it is in fact false. So that's a type 2 error. You want to memorize both of these because we are going to make references to these types of errors throughout this chapter and ones that follow it. And so you want to be really clear on what's a type 1 and what's a type 2. And then one of the ways that sometimes people use to remember this is they say a type 1 error is like convicting an innocent person. We have this claim H0 that is on trial, and to say that it's true is like saying that it's innocent, and then to reject it is like convicting it. So if you convict an innocent person, that's definitely a bad mistake. And then when we look at the type 2 error, we're saying HO is false. That's like saying the person on trial is guilty, but then we do not convict them, so we let them go free. And so a type 2 error is often referred to as freeing the guilty. And both of those are mistakes. So we're not trying to make a type 1 error or a type 2 error. We're trying to make correct decisions. We're trying to convict the guilty and free the innocent. But because we make our decisions based on sample data, which is subject to random variation, we can get misled at times and end up making the wrong decision. Alright, let's go ahead and look at an example that illustrates the different conclusions that we can reach and how that occurs, and then how the possible errors or correct decisions come about. So we're going to return to the snowboard binding problem where we said that our null hypothesis was that H0 was that mu equals $100, and we had an alternative that mu was less than $100. So suppose the data collected does not provide enough evidence to show that the average price of the bindings in April 2008 was less than $100, then what decision would we make? So the key here is that it says that we're to suppose our sample data does not provide enough evidence. And to show what? That the average price was less than 100. So there's not enough evidence to show H1. And we said right up here that if you do not have enough evidence to show or prove H1, you would not reject H0. So that line about there's not enough evidence to show the average binding is less than 100 indicates that our decision would be to say do not reject H0. Now when we move on to part B, it says suppose that it came out a different way. Suppose the data that we collected does provide enough evidence to show the average price of the bindings in April was less than 100. So this time the data does provide enough evidence to show. And to show what? To show H1, that the mean is less than 100. And again, if we come back up here and we read that it says when you have enough evidence to prove or show H1, that would be the time where you would go ahead and reject H0. So in this case, when there is enough evidence, our conclusion would be reject HO. And just remembering from what we've done before, for them to say there was not enough evidence probably means that either the evidence was on the wrong side or maybe it was just a small difference instead of a big difference. If they're saying there was enough evidence to show the average price was less than 100, then we must got a sample mean that was quite a large difference to the left of 100, since this is a left-tailed test. Now, suppose that it was later determined that the true average price for the bindings in April of 2008 was $97.18, then classify each of the decisions above as either a type 1 error, a type 2 error, or a correct decision. Well, I can already partially start to do that just based on this 97.18 number. When they say suppose that it was later determined that the true average, we have to remember that the true average is a reference to mu. So they're saying the true average was 97.18. That means they're saying that mu was 97.18. And if mu is 97.18, that means that HO, that stated that mu was equal to 100, would be a false claim, and H1, that says mu is less than 100, would be a true claim because the truth is less than 100. And so we're in the situation here where HO is considered false. So what does that mean about the way this test is going to turn out? Well, if we go to the chart, if HO is false, you could make a correct decision or you could make a type 2 error. You can't land over here because that only applies when HO is true. So it's either going to be a correct decision or a type 2 error for each of these. So now let's look at the different decisions we made and how that would play out in the chart. In part A, our decision was do not reject HO. And then we know from right up here that HO was false. And if you have the decision to not reject HO combined with HO being a false claim, is that good or bad? Well, if their claim is false, we'd want to reject it, but we didn't. So it sounds like an error to me. And when we do not reject a false claim, that's a type 2 error, and we can see that in the chart as well. HO is false, and we did not reject it, so that would be a type 2 error. Notice, based on the way I talk that through and also the way I'm drawing the arrows here, that it takes two pieces of information to decide if you've made a correct decision or an error. You have to know if HO is a true or false claim, and you have to know what your decision was. And once you have those two pieces, you should be able to put it together. So finally, if we look at the decision we made in part B, that was to reject HO. And if you reject HO, and if HO was a false claim, then is that good or bad? So if it was a false claim, we should reject it. So without even looking at the chart again, when it feels like we've done the right thing, that should be a correct decision. And let's verify it in the chart though. We have reject HO and it is false. So reject HO and it is false. That should be a correct decision. When you first start doing these in the homework, you may feel the need to go reference that chart and go ahead and do that as much as you need to. But eventually you need to reach a place where you feel like you can just process this through and think about, is it correct or is it an error? And if it's an error, then you need to have the two types memorized so you can distinguish what type it is. Alright, we're going to look at one final example here and try to put the type 1 error, type 2 error, and correct decision into words. So let's refer to the gas price example where it was claimed that the mean was equal to 3.097 and where we had an alternative that the mean was greater than 3.097. And they want us to explain using everyday language what it would mean in terms of the application and the evidence for the newspaper to make a type 1 error, a type 2 error, or a correct decision. So first of all, when you make it, they want us to write out a type 1 error, I'd want to think about what is that in terms of the definition. And a type 1 error is rejecting HO when it is in fact a true claim. So the first part I'm going to focus on is that I'd be rejecting HO. Why would I do that? Well, according to the chart from the previous page, we would only reject HO if there was enough evidence to prove H1. So that would mean that I did have enough evidence to show that the true average was greater than 3.097. So I would start off by saying it's a type 1 error if we have enough evidence to show the average price in California is higher than the national average. Notice that looks like H1. And that would not be a type 1 error by itself. That would just mean I was going to reject HO. In order for it to be an error, I'd have to be rejecting HO when I should not have, when it's a mistake. So what we want for this to sound like a mistake is for this last part to disagree with our evidence. We want the truth to disagree with our evidence. When that happens, we've made an error. So if we have enough evidence to show the average price in California is higher than the national average, when in fact it is not higher, then we would have made a type 1 error. So we're saying there the truth is California is no higher than the rest of the nation, yet our evidence points us in the wrong direction. If that happens, we're going to make a type 1 error. What about a type 2 error? Well, again, going back to the initial definition, that would be if we do not reject HO and it turns out to be false. So why would we not reject HO? Well, according to this, that would happen because we did not have enough evidence to prove H1. So when it talks about we did or did not have enough evidence, when your decision was to not reject, that would always be because we did not have enough evidence. So if we did not have enough evidence to show the average price in California is higher than the national average, that would mean we do not reject HO because we weren't convinced of H1. And that would be a mistake if we should have rejected HO, and that would be if this was really a false claim and this was a true one. So if we did not have enough evidence to show the average price in California is higher than the national average when in fact it is higher, then that would be a mistake as well, and it would be a type 2 error type of mistake. So both of these should sound a little awkward when you write them out. A lot of times people struggle with this because they're feeling like this just doesn't feel correct when I write it. But the thing that you have to realize here is you're trying to describe a mistake that's happened, so it shouldn't really feel like it fits. It's a mistake because the truth doesn't match up with our evidence. So here we had enough evidence to show the average price was higher, but it really wasn't. Here we didn't have enough evidence to show the average price was higher than the national average, but it really was higher. And you might ask, how could that possibly happen? How could your evidence disagree with the truth? And again, we have to remember that we're randomly selecting our sample and that we could be misled due to random variation there. So for example, if the California average was the same as the national average, we still might just in our random sample happen to pick places that are maybe in remote areas or big cities like San Francisco where the gas prices tend to be higher. And because we ended up with just kind of an unfortunate, unlucky sample of high gas station prices, we might get a X bar like $3.40, and we'd say, hey, that's way higher than this 3.097. We'd reject this, and yet it still could be that if we had a more representative sample, we'd have found out this was true. How does the type 2 error happen? That's actually a little bit easier. Suppose that California is just a little higher than the national average. We might get an X bar like $3.11. And while that does support H1, it's not a big difference, so we wouldn't reject HO because we didn't have enough evidence. And yet, it could still have been the case that California is higher, just not a lot higher. And so our evidence wasn't strong enough for us to reject. All right, correct decisions should be quick here to finish up. Correct decisions can be made in two ways, either when you reject or do not reject HO. So we could have a correct decision if we have enough evidence to show the average price in California is higher than the national average. We might also make a correct decision if we did not have enough evidence to show that the average price in California is higher than the national average. For it to be correct, we want the truth situation to match our data. Instead of being contradictory, we want them to agree, and that's what makes it correct. So if we have enough evidence to show the average price in California is higher than the national average when in fact it is higher, that would be a correct decision. And if we did not have enough evidence to show the average price in California is higher than the national average when in fact it is not higher, then, when in fact it is not higher, then that would be the other possibility for the correct decision. So two ways we can make a correct decision, one way for type 1 error and one way for type 2. I think you'll find when you first start trying to do these in homework, it's a little hard to just write out these full sentences from scratch. So you might want to turn back to this page and look at these examples as a template as you write out your first few. And we'll keep practicing this as we go through sections 9.2 and 9.3 and even in chapter 10 and 11. So the more you do, the more you want to start to be able to get to where you don't need your notes to look at it, but at first you might need the template to get off to a good start.